So in this video, we'll be looking at Newton's method. So suppose we want to approximate the root of a function f of x, i.e. we want to find an x star where f of x star is equal to 0. So we want to find the x-intercept. Suppose now we have an initial approximation to this root and we call it x naught. So that can be represented by this purple highlighted bit on the graph. Now suppose we want to find the tangent line of f of x at this approximation x naught. Well, we can do that by finding the gradient between this x naught and the x-intercept of our new tangent line. So our gradient at x naught will be equal to our change in y over change in x, so it will be 0 minus y naught over x1 minus x naught. And this can also be rewritten as f at x naught over x1 minus x naught. If we isolate x1, we'll get that x1 is equal to x naught minus f at x naught over f prime at x naught. And Newton discovered that we can do this iteratively many times to find a iteratively more accurate approximation to a solution. So Newton's method says that if xn is an approximation of a solution f of x is equal to 0, and the derivative f of xn is not equal to 0, then the next approximation to the root is given by the equation we've just derived. So as we get more and more iterations of Newton's method, we find more accurate approximations to the root. So in this case, x1 is more accurate than x naught, and x2 is more accurate than x1. So let's look at an example. Use Newton's method to find the second approximation to the solution of cos x is equal to x that lies in the interval 0 to 2. Here, our f of x will be equal to cos x minus x, because we're finding the solution, so we equating it to 0. And let's say our initial approximation lies in the midpoint of our interval. So our initial approximation, arbitrarily, is 1. So let's use Newton's method to find the first approximation to the solution. So in this case, x1 will be equal to x naught, which is 1, minus our function value at 1 over the derivative of our function at 1. This will be equal to 1 minus cos of 1 minus 1 all over minus sine 1 minus 1, where we've calculated f prime of x to be minus sine x minus 1. If we plug that into our calculator, we'll get something like 0.750364. So let's find our second approximation to the root. Using Newton's method, x2 will be equal to x1 minus f of x1 over f prime at x1. Well, we've calculated x1 to be 0.750364 minus cos of this terrible number, 0.750,364 minus 0.75 da 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 over minus sine 0.75 da 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 minus 1. And you should get a final value of 0.73 something, 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 something. And that is Newton's method, and this is our second approximation to the root of cos x minus x.